Welcome to our presentation. In this presentation, we'll introduce our work, HeLiMOS Dataset, a dataset for moving object segmentation in 3D point clouds from heterogeneous LiDAR sensors. Moving object segmentation using a 3D LiDAR sensor is crucial for 3D scene understanding and identifying moving objects. Recently, diverse types of 3D LiDAR sensors have been developed, including mechanically spinning, prism rotating, solid-state, frequency-modulated continuous wave, FMCW. As a result, the generalization performance of MOS approaches has become important. However, we see that existing public datasets have two limitations for evaluating the generalization capabilities of heterogeneous LiDAR MOS. First, existing heterogeneous LiDAR datasets do not provide point-wise MOS labels. Second, multiple datasets with point-wise MOS labels are only acquired by a single omnidirectional LiDAR. To tackle these limitations, we propose HeLiMOS, a novel moving object segmentation dataset for heterogeneous LiDAR sensors. Our contributions are threefold. To provide a clear context, we will now explain each of our contributions in detail. Our first contribution is that HeLiMOS provides point-wise MOS labels and shows novel characteristics not found in existing datasets. HeLiMOS is derived from the Case 05 sequence of HeLiPR, which contains a variety of moving objects and revisits the same locations multiple times. HeLiMOS inherits these characteristics. By containing a variety of dynamic objects, HeLiMOS provides a point-wise MOS labels captured from different LiDARs. Additionally, compared to other MOS datasets, HeLiMOS shows a significantly higher ratio of dynamic points across all LiDAR sensors. Moreover, by revisiting the same locations multiple times, HeLiMOS shows diverse dynamic point patterns within the same locations. Our second contribution is a novel, efficient, automatic labeling framework. Labeling moving objects is highly labor-intensive and time-consuming for human labelers. To alleviate this burden, we propose merging and splitting-based and instance-aware labeling frameworks. First, let's start with the merging and splitting-based framework. We synchronize the scans from the four LiDAR sensors by merging them into the ouster frame. After labeling the synced scans, we backpropagate labeled results to the individual point clouds. This parallel process allows more efficient labeling of the 4 point clouds compared to sequential labeling. As mentioned in the previous slide, our dataset includes multiple revisited scenes. Therefore, if we label the revisited scenes all at once, it would be more efficient. However, even though we use the provided ground truth poses to merge revisited scenes all together, we found that undesirable pose errors occurred in revisited scenes. As you can see in this figure, when we align the submap from the first visit with the submap from the fourth revisit, incorrect discrepancies appear. This inaccuracy negatively affects the MOS labeling because it can be misunderstood as moving points. To solve this, we propose topology-based trajectory clustering and submap-based pose correction. We divide each trajectory into clusters based on its revisit frequency. Taking cluster A as an example, each trajectory belongs to subcluster C1, C2, C3, and C4. Next, we build submaps from subclusters and then apply submap to submap ICP to correct the poses by aligning them to a reference frame. Through this process, we can get more globally aligned poses, which are suitable for MOS labeling. Now let's take a closer look at the steps in our instance-aware labeling framework. To generate the initial MOS labels, we used Erasor2, a state-of-the-art static map-building method. Erasor2 performs instance segmentation and detects moving objects at the instance level. We found that Erasor-2 achieves a higher static mapping performance compared to other methods that do not consider the instance information. This is why we chose Erasor-2 for the initial labeling method. Static map building methods, including Erasor-2, tend to aggressively detect moving objects. Therefore, some static points in the initial label are wrongly classified as dynamic points. To solve this problem, we use multi-object tracking-based filtering. Moreover, we propose a bounding box augmentation to reduce the number of false negatives, which are originally moving but classified as static. Therefore, even with just our automatic labeling, we can get sufficient high-quality labels. After automatic labeling, we also perform a human refinement process to enhance the quality of the final MOS labels. Our final contribution is providing novel benchmarks that could not be evaluated using existing datasets. We evaluated the state-of-the-art MOS approaches, including 4D MOS and MapMOS, as the initial benchmarks in our dataset. Both models achieve significant performance improvements across all sensors after being trained with our dataset. At the same time, the noticeable performance differences across sensors suggest that there is still room for improvement in heterogeneous LiDAR moving object segmentation. In conclusion, here's a brief summary of our key contributions. In this paper, we presented a novel moving object segmentation dataset for heterogeneous LiDAR sensors. We also proposed an instance-aware automatic labeling framework to reduce the time and effort required for human labeling. Finally, we evaluated state-of-the-art MOS approaches as initial benchmarks in our dataset. Through this work, we suggest the necessity of a heterogeneous LiDAR dataset for moving object segmentation and suggest new research directions towards sensor-agnostic segmentation.